Hello, welcome to Notes 11.04. Today we're modeling using volume with some real-world applications. Looking here at exercise 1. A thermal insulating sleeve is used to cover the lateral surface, or the outside, of a hot water tank or hot water heater to help improve the efficiency. The hot water tank is a cylinder with a 13-inch radius and a 75-inch height. So the water tank is what's inside the center here. The sleeve that kind of surrounds that water tank is 3 inches thick. The insulating material that makes up the sleeve is a fiberglass composite. How many cubic inches of fiberglass composite are needed to create a sleeve round to the nearest tenth of a cubic foot? So their units are a little backwards here. But what we're going to end up doing is having inches, or the measurements they gave us, and we're going to need to round to cubic feet at the end. So what we're going to do here first is find the volume of the water heater and sleeve together. So the volume of the whole cylinder, so if we include the water heater inside plus the sleeve, we're going to have a radius there of 16 inches. From the center, the water tank itself is 13 plus the 3 more of the sleeve. So our first radius is going to be 16. Its height is 75. And then just the water tank inside has a radius of 13 inches and a height of 75. So essentially what we're going to do here is find the volume of the whole object, so the water tank and the sleeve, and then we're going to subtract out the core. So you almost kind of got to think of it as the water tank comes outside of the sleeve, so that we're just left over with the volume of the sleeve measurement. So then we're going to subtract the volume of that centerpiece. Now, again, I'm going to talk about the units here for a second. These are in inches. So remember, 1 foot cubed, or 1 cubic foot, equals how many cubic inches? So if we think about a cube for a second, that would be 12 inches over, 12 inches back, and 12 inches high. That would be 1 cubic foot, a foot by a foot by a foot. So 12 times 12 times 12 is 1,728. So we're going to need that conversion a little bit later. So 1728 inches cubed equals 1 foot cubed. So moving down here on the screen, we're going to find the volume of the whole cylinder and volume of the center. So again, cylinder, the volume equals pi r squared h. So we really only needed the radius and the height here. So we're going to have pi times 16 squared times a height of 75. And then we're going to subtract pi times 13 squared times 75. So that's going to give us cubic inches, because we're really taking inches squared times 75 more inches. And that difference, now you could type them in each individually. I'm going to write some decimals down here for you. But this ends up being 60,318.5789. The second volume ends up being 39,819.68. So when you subtract those, 60,000 subtract about 40,000, you get 20,498.89 something. I'll have those 2 decimals written down. Now, one thing I will say is I would highly suggest just typing the all into the calculator at once. So you can see here I typed in pi times 16 squared times 75 minus pi 13 squared times 75. You don't need each decimal written out. I would write out your substitutions and put it in all at once. But again, here we have inches cubed, and they ask for nearest cubic foot. So what we're going to do is we're going to take our inches cubed and we're going to do a conversion with that 1728 from before. So looking here, how I write this is the 2498.89 8920, I guess, were the 4 decimals, inches cubed gets multiplied by a scale factor of 1 foot cubed is to 1,728 inches cubed. So I know we did some unit conversions on one of our first assignments, but remember, inches cubed in a numerator will cancel with inches cubed in a denominator. So we're going to end up dividing. So 20,498 divided by the 1728, I'm just going to shift it over to show you the division, will end you with an answer of 11.9 feet cubed. And that's going to be our final answer here for number 1. Moving down to exercise 2. Talking about a silo for storing green. So farmer is building a new silo for storing green. He is comparing the silo with a cone top to a silo of a hemisphere top. Which silo has a larger volume? So let's look at some of the dimensions. So the first silo has a diameter of 18. It's going to be a height of 60. So both heights were the same. The height of the cone here is 9 feet. The height of the dome would be 9 feet as well. Now, most of you are going to say the hemispherical silo is going to have a larger volume. Okay, and the reason being is that cone takes up more space than this. I'm sorry, the hemisphere here would take up more space than this cone would, because the cone kind of comes to a pointy top, where the hemisphere has that rounded extra section to it. So that's one reason that the hemisphere top will be bigger. But also, if we look at the volumes, so I'm going to look to make some substitution for the volume of the cone silo. It's going to be my first line here. Now, the whole silo is really a cylinder plus the cone. So in the last example, we were subtracting some volumes. Here, we're going to take the volume of the cylinder, which is pi r squared h, plus volume of the cone, which is a third pi r squared h. So if I make our substitutions, we have pi times our radius would be 9, because again, the diameter is 18, squared times a height of 60 feet, and everything wasn't measured in feet, so we're just going to stick with that, and added to the volume of the cone up top. Its radius, again, is going to be equal to the radius at the bottom of the cylinder, and its height, they gave us over here, is 9 feet. So we have a third times pi times 9 squared times a height of 9, which would end up being, remember, 9 cubed at some point. So that's the volume of the cone top. Now I'm not going to calculate that out quite yet. I'm going to make the substitutions for volume of the hemisphere top. So again, volume of the cylinder base from here down is going to be the same. So we have pi times 9 squared times 60 added to, now volume of a hemisphere, and I'm going to do some work way up here at the top of our page, is 4/3 pi r cubed. But we're going to take that whole thing and multiply it by a half. So when I multiply these two fractions, we get 4/3 sixths. Okay. So I'm just going to write that as 4/6 pi times 9 cubed. Because if I write it like that, we can kind of compare the volume of the two silos here, because the only calculation difference is that the cone top is being multiplied by 1/3, the hemisphere top is being multiplied by 4/6. Now we know 1/3 is really 2/6, so this hemisphere top almost has 1/3 more, if you figure about it, because this would reduce to 2/3, has 1/3 more space in it than the first one would. So which silo has a larger volume? For the first part of this question, just looking at the equations, we're going to say the hemisphere. Now part B asks how much volume, by how much does the volume of the larger silo exceed the volume of the smaller, is where we're actually going to calculate them out. Okay, so looking here, I typed each one in. So pi 9 squared times 60, and I'm sorry, this is backwards, times 1/3 pi. So the cone ones on top is about 16,031. Volume of the dome top, the hemisphere top, is 16,794. If I subtract those two answers, and I can write them down here for you, we get, helps if I pick up the pen, this block. So 16,794.954.3 subtract 16,031.5473 leaves us with a difference of about 763.40 is how I'm going to leave that answer to the hundredths place. Now at the bottom here, we're looking to find a cost. So this is where we have to decide how these conversions are going to work for us. So this second answer, I believe, is what we're going to be going with. The cost of building a silo depends on its holding capacity expressed in bushels. So corn or grain is measured in bushels for farmers. These silos fall into a price range of about $2.21 per bushel capacity. What is the cost of the smaller silo? And what that means is, what's the cost of the, what's the price of the amount of bushels we can fill in there? So we're going to use that second volume here, which is the 16,031. And we're going to use the scale factor that 1 bushel is approximately 1.24446 cubic feet. I'm sorry. So 1 bushel is this amount. So if we start with our volume, which is 16,031.5473, and again, that's measured in feet cubed, we're going to multiply by a scale factor of 1 bushel is to 1.24446 feet cubed. So again, I took that scale factor and I made it a ratio. So that feet cubed is in the numerator and feet cubed is in the denominator. So if I multiply across here, now I'm going to set this over 1. When I multiply across, I get my 16,000 in the numerator and 1.2446 in the denominator. So you're going to take your 16,031 and divide by 1.24446, and our answer ends up becoming 12,882.33 bushels. Now that's how many bushels we have. We have about 12,000 bushels, but the cost per bushel is about $2.21. So here, we're going to multiply by $2.21 per bushel, And our final answer for this question is the cost of the smaller silo with its 12,000 bushels it could hold, or almost 13,000, is going to be $28,000, 469. And this is where you have to make sure you're rounding correctly. Money is rounded to the hundredths place. So it's going to end with 95 cents. Now, I highly suggest you multiply and divide this out so you kind of remember the process. The more you do it on your own, the better off you are. So moving on to the notes. So those were 2 modeling problems. The notes here have 3 questions. I'm only going to do 2 of the 3. I'm going to skip number 2 for today. But reading number 1, the average amount of pasture needed to feed a mature mule is 1 acre per mule. A farm has 3 rectangular fenced pasture sections. One pasture section is 100 feet by 300, the next is 150 by 500, the third is 250 by 400 to be used for grazing. 6 mules are being adopted from the rescue program. The farm does not have sufficient pasture space to support 6 mules according to the 1 acre per mule guideline. If there are 43,560 square feet in 1 acre, what is the least amount of additional square footage of grazing that will need to be fenced in per this guideline? So if we have 6 mules that each need an acre, that means we need 43,000 square feet per mule. So what we're going to do is we're going to stick with feet for a minute, and then we can subtract to find how many cubic feet we have to how many cubic feet we need for 6 mules. So here we have 3 rectangular pastures. One was 100 by 300. So its cubic feet is going to be 30,000, right? Because we're going to multiply length times width. The second pasture was 150 feet by 500, and 15 times 5 gives us 75,000 feet cubed. And the third pasture was 250 feet by 400 feet, and that would give us 100,000. There we go, feet cubed. So the total square footage that we have as of this moment is 205,000 feet cubed. So that's how much pasture space we have to start with. Now, when we have 6 mules, and each mule needs about an acre, which is 43,000 feet, 43,560, we're going to multiply that. So if we need 6 acres, we're going to find the total square footage for the amount of acres is 261,360 feet squared is how many we need. Now we have only 205,000. So the additional square footage we would need is about 56,360 feet squared. So again, the question is long and wordy, but we essentially find the areas or volumes of what you need and did do some subtraction or addition from there. So like the first question we had today was the thermal insulating sleeve. We needed to take the volume of the big shape, subtract the volume of the small shape on the inside, and convert from inches to feet cubed. The second question, we had to add volumes together instead of subtracting. Here we had to add some areas together. The next question has a lot of conversions necessary. So I'm going to try to word it out. So number 2 here, we're going to skip. If you want to try it on your own, you can. I'll tell you the answer, final answer, if you do want to try it on your own just for extra practice, is 45%. It's talking about a body mass person's average density. So it's a good science related question, but for timing today, I decided to skip that one. So looking at number 3, a kitchen was remodeled and granite countertops were installed. A regular island in the kitchen now has granite top measuring 5 feet by 8 feet by 1.5 inches. So if we're thinking about a countertop here, okay, it's going to be 5 feet deep by 8 feet long, and its depth is 1.2 inches. Okay, the density of the granite, and when you read the word density, you should be thinking density equals mass over volume. We're going to need is 2.7 grams per centimeter cubed. How much does a granite top on the island weigh in pounds? Round to the nearest pound. So a few conversions and a few issues we're encountering here is that the measurements they gave us were feet and inches. The density conversion is 2.7 grams per centimeter cubed. So a little note I'm going to write here is we're going to convert our feet and inches to centimeters first. Okay. I know at the very first question we converted at the end, but since we have multiple measurements we're looking at here, we're going to convert to centimeters first, because if we find our volume is blank centimeters cubed, we can go into our density formula very quickly to find out what the weight is in grams. But then we're going to have to convert grams to pounds at the end. So I'm going to look at that conversion in a minute. So first and foremost, we have feet. So we have, so I'm going to do some work over on the side here. We have 8 feet, and we need to convert that into centimeters. So 8 feet is going to be multiplied by, well, there's 1 inch. I'm sorry, there's 12 inches in 1 foot. Start this over. It's very messy and I'm going to run out of space. Sorry about that, guys. So let's go back. We have 8 feet and we're going to multiply by 12 inches in 1 foot. And another conversion that you'll find on your reference sheets is that 1 inch equals 2.54 centimeters. So 1 inch equals 2.54 centimeters. So that's our conversion here. Feet will cancel with feet, inches will cancel with inches, and I'm left over with our centimeters. So 8 times 12 is 96 times 2.54 gives us 243.84 centimeters. So that's the entire length in centimeters. Then we have to convert our 5 feet times 12 over 1 times 2.54 over 1 will give us 152.4 centimeters. And our last conversion is our depth of 1.2 inches. Now here we only need to multiply it once, but 1.2 inches gets multiplied by 2.54 centimeters per 1 inch. So 1.2 times 2.4 gives us 3.048 centimeters. So that's our length, our width, and our height, or depth, really, of our slab. So volume equals length times width times height. So for a rectangular prism, we're really finding the area of the base times the height. So that LWH formula that you've known since middle school kind of fits our pattern with the capital BH here. So when we multiply our three volumes together, our three dimensions there together, the volume ends up being, I'm going to change colors, 113,267.3864. And that's centimeters cubed, remember, at the moment. So that's our volume. Now we need to find its weight in pounds. So density, again, equals mass over volume. Give us some space down here. So density, remember, equals mass divided by volume. And we're trying to find the mass, right? Mass is a weight. So our density is 2.7 grams per centimeter cubed. So we're going to take density times our volume equals our mass when we kind of multiply there. So the density is 2.7 times our volume. I'm just going to kind of draw an arrow for a second. Equals the mass should be so 2.7 times the 113 is going to give us 305,821.9432. And again, our density was grams per centimeter cubed. So right now, this measure will be grams. So if we have about 305,000 grams and we need to convert to pounds, there's two conversion factors that we're going to need. Well, 1,000 grams equals 1 kilogram. So we're going to convert to kilograms. And another conversion factor we can find on a reference sheet is that 1 kilogram equals 2.2 pounds, LBS for pounds there. So that's our conversion factor. So if we have about 305,000 grams, that would be 305 kilograms. So here, to go from grams to kilograms, we're going to divide by 1,000. Because again, we're going into a smaller unit, so we have to divide. So our decimal moves over a few places, and we get 305.8219 kilograms. And we're going to use this kilograms to pounds ratio by multiplying, and we're going to make it that a ratio. A fraction is what I mean. So 2.2 pounds LBS, I know it looks like 1 BS, but it's pounds, is to 1 kilogram. So that's how we use our conversion factor so that kilograms cancel and we're left over with pounds. So 305.8219 gets multiplied by 2.2 and we get 672.8 pounds. So that granite countertop is pretty heavy, 672 pounds. Okay, so that's the end of the notes for today. Please try what you can on the homework. They're going to be 3 modeling questions. I'd like you to choose 2 of the 3 that you'd like to try, depending on what formulas you're comfortable with. If you'd like to do all 3, we can count the 3rd one toward extra credit. Good luck. Thank you very much.